Hi everyone, welcome to our video for Activity 6. This week we are talking about t-tests. So if you remember, the base idea of t-tests is that you're comparing two means, okay? And these means are going to either represent a comparison between a sample and a population, or an estimate of a population, or we could also be looking at two samples where we have a control group versus an experimental group, and we're wanting to know what the difference is between those two groups to see if a treatment has an effect on a certain outcome. Okay, so since we are slowly approaching our next exam, this week I've kind of built in some review questions so that you have more practice kind of incorporating some of the skills and running tests that you've already gone through. Also, some of the content for this exam has a little bit of crossover from exam 1, so there's some refreshers on different calculations that you guys have already done previously. So if you get stuck on the review stuff in particular, feel free to go back to previous activities to refer to how to do certain things. For those particular spreadsheets, I'm kind of going to skim over them, give you some hints on how to do some of your processes, but overall it's primarily meant for you to review the material and make sure that you really understand it. So for those particular spreadsheets, especially the ones that would apply to correlations and regressions, if you want to wait until you get your Activity 5 feedback, that might be a wise decision, just in case there's any common mistakes that pop up or any comments that I put in your feedback that could be helpful. Okay, so that's kind of the general rundown of how the activity is going to work. So for this first spreadsheet, we're going to be running all of the different types of t-tests and going over how to read them. We're also going to be calculating effect size as well as sample size. So we had these formulas in the lecture. This is where we're going to get to apply them since we didn't have any practice examples in the lecture slides. So we're going to be operating a single sample t-test, independent t-test, as well as a dependent or paired samples t-test. I've included all of the pathways for these. You can also find these pathways in the, or a little bit more detailed description of these tests in your Module 8 Key Terms and Concepts document in the supplemental resources area for this week's content. But basically we're going to have 4 sets that we'll be working through. And based on a given scenario, we have to figure out how we're going to test this information. Okay, so let's go ahead and start with data set number 1. We're looking at vertical jump values that were taken from a sample of female CSULB students. And we want to compare those values to the college age average of 12.4 inches. Okay, so this is a good example of hopefully you guessed it, a single sample t-test, right? Because we're saying we have a sample of female students, right? That's indicating one sample. And we're comparing it to whatever we're estimating as the college age average of 12.4. So we have a mean to compare against, okay? So basically what we do is we go into our data set, right? And we'll just say all of this data is going basically to represent our collected sample, right? So I'm going to go ahead and copy this. And I have SPSS already pulled up, so we're just going to paste it into here. okay? Pretty simple, right? We should have vertical jump representing, or all of these data points are representing individual people, and they are ratio data, right? But the pathway you can see here is okay. Analyze, compare means, which makes sense because we're comparing means, and we will find a one sample t-test. Okay, so the book refers to it as a single sample, SPSS is one sample. I figure it shouldn't be too difficult to distinguish, right? So we do compare means. We've run a means analysis before, so that should look familiar, right? And then this is where we find all of our t-tests. So we're going to do a one sample t-test. Our test variable is going to be vertical jump. And then our test value is going to represent what our estimated population mean is. In this case, we identified that as 12.4. So you just type 12.4 in the test value box. We would press options. Basically, the default is 95%, right? If for any reason I told you use a 90% or use a 99%, this is where you would go to change it. Okay. Other than that, this test is pretty simple to set up, right? We just insert our variable, insert our estimated population mean, and we press OK. Right? Because we're going to get a lot of t-tests, I'm just going to put dataset 1 so that I can identify this in the output. And this is the simplest form of an output that you're going to get for t-tests, pretty much. Okay, so you'll get your descriptive statistics. You can see we have the standard error of the mean, which we calculated in class, right? And used this value in order to find what our t-statistic was, or what our t-value is. So this would represent the calculated t-value. Okay. Our degrees of freedom, remember, is calculated by looking at the total number of people in the sample. So in this case, it's 98. And we subtract by how many samples we've collected, which in this case is 1 because it's a single sample test, right? So our degrees of freedom should be 97. That checks out. And then if we looked up 97 degrees of freedom at a 95% level of confidence on our t-table, we should find that our t-statistic, right? Remember, we always take the absolute value of this because there are no negative values on the t-table. So we would be comparing 2.237 to whatever the critical value is at whatever's close to 97 degrees of freedom and a 95% level of confidence. Now we use the t-table to estimate if we have significance or not, and you'll notice in here this says sig two-tailed. So this is our p-value for a two-tailed test. Okay, whenever you see sig in SPSS, it means p, right? But in a table, we can estimate what our p-value would be. In SPSS, we actually get an exact p-value. So in this case, we have a p-value of 0.028, okay? And I'll let you guys determine if you think that is significant or not based on the level of confidence that we used, okay? For practice, if you guys wanted to use these descriptive statistics to calculate the confidence interval, see if you get something similar, that might be a good idea. But generally, this one's pretty basic to read. Okay, so on, oops, I'm in the wrong Word document. So within these t-test questions, there's some values that you'll have to write down. For this one, I think VOMAX testing, the vertical jump testing would only play a role in question A, right? If you're saying which data sets out of the 4, this is the only question that's specifically looking at all 4 data sets. Okay, everything else is specific to data sets 2 through 3. So primarily you just need this one on your output, understand how to run the test, and you're good to go. Okay. One down. All right. Now we're going to look at data set number 2. This is where we'll get a little bit more technical with our processes. So we're looking at VO2 max testing in USA individuals as well as Canadian individuals. Specifically, we're looking at elite runners. Okay, so we took the max VO2 max values for each of these samples. Okay, you can imagine or think, right, how remember, if we're working with t-tests, we've identified what type of independent variable we're working with, what type of dependent variable we're working with, right? How many levels of our independent variable? Clearly we have 2 levels, right? And it's based on geographic location, we could say, right? So we can kind of create a legend over here. I can't spell. We can create a legend that tells us what certain values mean. And actually, I'm going to move this over here. Or I'm going to move it up here. That seems like it's better. Oh, just kidding. I guess here is good as anywhere. So with this, we can say USA, let's say, is equal to a data label of 1. And Canada is going to be equal to a data label of 2. So we've identified group 1, group 2, or sample 1, sample 2. And then remember in SPSS, when we put our data into a data sheet, each row has to represent a single individual, right? So because we have separate measurements for USA or the USA sample, and separate measurements for the Canadian sample, we'll have to stack these values on top of each other so that they will represent, right, the entire set of individuals that we've actually measured, instead of reading across that each person was measured twice, because that's not the case here. Okay, so for USA, we can just go ahead and label all of these as 1. And then just for ease, I'm going to copy the Canada values down here and then just label those as 2, right? So basically from here, we can copy this data. We'll go back into SPSS and we need to create a new data sheet. Okay, so I'm going to close the first one. And again, I would recommend saving the data sets just in case you have to change anything. In this case, I pasted without variable names because I didn't have variable names. If I go back to here, you can see it's a little jumbled, right? So basically we have to say the first column is going to represent, oops, there we are. The first column is going to represent the country. Oh wait, I want all of that deleted, right? So within this, we can say we have certain values where 1 is representing individuals from the US and 2 is representing individuals from Canada. Okay. Variable 2 is going to represent our VO2 values. Oh my gosh. VO2 max. Okay. We can make sure that these are set, right? Country is actually going to be nominal data, whereas our VO2 max is measured data, so that would be scale or ratio. Okay. So from here, we then can run the t-test that we think we should. And if you've riddled it out, since we have independent samples, we should have drum roll, you guessed it, an independent t-test. Okay, so we'll go to Analyze, Compare Means, and you'll see we have our independent samples t-test. In here, you'll see test variables. This is going to be similar to the single sample t-test. So in this case, test variable is going to be the dependent variable, which is VO2 max. Our grouping variable is what it sounds like, how we grouped our individuals. So you're just going to pop that into here. And then you'll notice there's these two little question marks. So after you put your grouping variable in, you have to define your groups. Okay, we've specified that country labels are going to be numerical values, right, that represent either USA or Canada. So you're just going to define who's group 1, which we just say is value 1, and group 2 is going to be value 2. Okay, so you just press continue. Again, if you click options, it's going to give you the same information as the single sample t-test. So default, again, is always going to be 95%. So we'll just leave it as is. Press OK, and then we get our t-test result. And I'm going to change the name to dataset 2. And then you can see it gets a little bit messier, or there's a little bit more information. Okay, so we still have our descriptive statistics here. Okay, so we can see there were 25 individuals in each group of runners. We can see what their mean is, their standard deviation, standard error of the mean, right? And then we end up seeing this table. So the independent samples test is your t-test result. Okay, there's a little bit more information added onto here. Okay, so you can see Levine's test for equality of variances. This is our homogeneity of variance test. Okay, and it only encompasses these two boxes. Okay, so all you're really concerned about is the value in this SIG column. Okay, so to answer this question, you need to know what the null hypothesis is for Levine's test, or for the homogeneity of variance assumption, right? Because remember, we have, for an independent t-test, there's 4 assumptions that we have to meet. We have normal distributed data, we have random sampling, the characteristics of our variables, right? So parametric dependent variable with a non-parametric independent variable that only has 2 levels, okay? And then we also have our homogeneity of variance if we're doing a between subject design, right? So we have to make sure that our samples or the sample variability is roughly the same in both groups, okay? So with this value, that's going, based on your evaluation, right, of this p-value for the homogeneity of variance assumption, you will say either equal variances are assumed or equal variances are not assumed. So you guys are going to decide what this means, or right, what this p-value means, and that will tell you which row to read. Okay. After you determine which row you're reading, you'll notice there's the t-statistic, degrees of freedom, and then we have our p-value for our independent t-test right here. Okay, in this case, the p-value is going to be the same for both of these rows. That's not always going to be the case, right? So because these values are the same in your answer sheet, I have added in this lovely little table, okay? And you're going to indicate what the p-value is for the test of homogeneity of variance, and you're going to indicate what that p-value means in terms of the table, right? And how you're going to read it. So hopefully that will help to clarify your choices, okay? But based on your p-value that you choose, you have some questions that you'll be answering, and that pretty much sums up for data set number 2. So not too difficult. Okay, I'm gonna go ahead and minimize data set 2 for that one. And we'll move back to our instructions and look at data set number 3. So now we have squat testing as our dependent variable, right? Or we're looking at 1RM values measured as a percent of body weight for members of the rowing and cycling clubs. Okay. For this data set, we're going to, again, assume that these individuals do not belong to the same group. Okay, so similar to our other example, we need to have data labels. So let's say that our rowing club will be data label 1, and our cycling club will be data label 2. Okay. Again, if we're using independent samples, when we go into SPSS, each row represents a single subject. So we create our data labels very similarly to the previous example, right, where we copy our data and then say all of the cycling people get a label of 2, right? And then we can copy this data into SPSS. This shouldn't be too difficult. Right, so before we do that, let's make a new data set. Okay, again, because I didn't copy with variable names, I'm just going to paste here, and then we're going to reset our variables. So this one would be sport club. Oh, and one tiny thing. When you type stuff in here, you can't have spaces, so I'm going to use an underscore. It's a very odd thing, but that's the way it works. Okay, our values, remember we said 1 was rowing, 2 we said was cycling, right? We have to make sure this data is inserted as a nominal measurement because we have categorized our subjects based on certain criteria. And then our other measurement was squat. We'll just put squat, okay? And that should be listed as scale, right? Because it's ratio data. If we had a measurement of 0, that would mean we have not actually collected on the person, okay? So similar to our previous example, right, we have 2 independent samples. Therefore, we're going to run an independent sample t-test, okay? So again, our test variable is our dependent variable, which in this case is squat. And our grouping variable is how we sorted our individuals. In this case, group 1 matches up with label number 1. Group 2 will match up with data label number 2. So this is rowing and cycling. Okay. Press OK, we get our t-test. This is data set number 3. Right? And then the same thing goes where we see our descriptive statistics up here. The reason why I use this example is you can see that the sample size is quite different, right? There's a difference of 20 individuals from one club to the next. So if you recall, when we have more people in our sample, we're expected to have less variability. When we have less people, we're expected to have more variability, right? So you should see a direct response in the results that you get in your t-test, right? Again, we're going to evaluate Levine's test for our homogeneity of variance assumption. Based on the p-value, you're going to decide if you have equal variances or not equal variances, right? That'll tell you which row to read. And then you'll look at your SIG table or your SIG column, right, for your t-test. And that will give you the p-value for the main effect of the t-test. Okay, and that's it. T-tests are you're going to love these or learn to really appreciate t-test outputs once we start getting into more complex outputs. Okay, but basically, if you know where to look for specific p-values, it shouldn't be too crazy to try to navigate. Okay. Our last data set, we're looking at VO2 max estimates. So we have a group of participants were asked to complete tasks for determining VO2 max using 2 different protocols. So Bruce treadmill protocol in the lab, as well as a 2K rowing test in which their time was used to estimate VO2 max. Okay, so in this case, one single group of participants, right, were basically given 2 different protocols, right? So if we're using the same subjects to measure a dependent variable, right, that's a within subject design. So when we have a within subject design, we literally just copy from Excel, and then we go to SPSS. Again, I need to create a new data sheet. And this time I can paste with variable names, right? And then, like we said before, if each person is measured once, this row represents the measurements that were collected for subject number 1, right? So if each person was measured twice, then we should have 2 measurements per subject. Makes sense, okay? In this case, both of our variables are going to be listed as scale. You can see the little ruler here. Okay, and this is because the values that are in those columns are representing ratio data, right? The actual classification or categorization of our variables as far as our independent variable of protocol is going to be the type of test that they were given. So the 2K rowing time versus the Bruce treadmill. But in a within subject design, those categories are going to be classified in the actual variable names instead of having a separate column for data labels. Okay, so if we're using the same people in both comparative samples, that means we have a dependent t-test or a paired samples t-test. Okay, and then this one's pretty simple as far as putting the data in. Basically, we're concerned with differences between the 2 means. So all we have to do is put both of those in there. Okay, the order that you put your values in is the order that the difference is going to be calculated. So if we take the mean of the Bruce protocol, it would be subtracted from the mean of the rowing protocol. So it really doesn't matter what order, right? We could put 2K rowing or Bruce treadmill. It doesn't matter what order you put them in. It's the way that you read the output that's important. Okay. Again, the options is still going to be the same setup. So we really don't have to touch that for any of the t-tests. So we'll press OK, and now we have data set 4 in our output. Okay. So with a dependent t-test, we're going to have pretty much the same assumptions that we have for a regular t-test, right? Or a regular independent t-test, such that we have normal distribution, random sampling, and we know what type of data our independent and dependent variables are representing, as well as the fact that we only have 2 levels of an independent variable. Okay, so in this case, independent variable is protocol, and we have either the Bruce protocol or the rowing time, right? So in addition to this, remember for independent sample, t-test, we have to do homogeneity of variance to make sure that our independent samples are relatively similar enough that we can actually compare them in a statistical test. In a paired samples t-test, instead of looking at homogeneity of variance, we have to look at correlations. Okay, so if you recall from the lecture, and remember I put in 2 different pairings, so basically this is the same information, it's just going to be reversed, right? If you look at the tables, the numbers are the same, they're just flipped based on how these pairs are oriented. So I'm just going to focus on pair 1 for simplicity. Okay, so we have to say, basically, if you're looking at an individual for the Bruce protocol, their VO2 max should be relatively similar based on their rowing time protocol, right? So we should expect a relatively strong correlation if an individual was tested with both protocols, right? So our criteria is that our correlation coefficient needs to be greater than or equal to 0.8 in order to be accepted, right? In which case we do have a strong correlation, so we pass that test, right? And then we can look at our paired samples t-test. Okay, so down here, it's a little bit different setup than our independent t-test with the respect that the mean difference is listed in this first column. And I know it's a little bit confusing because it says mean, but this is going to be the mean difference. So if we look at our table, right, so still looking at, let's look at pair 1, right? Like I said, the order that you insert is the order that they're subtracted. So if we do Bruce protocol minus 2K rowing time, that would be 52 minus 53. That gives us -1. Okay? So negative in this case is just indicating which variable had the higher average, okay, which would be the rowing time, right? If we flip that and we looked at pair 2, we're still subtracting the same numbers, but rowing time, which has the greater mean, is being listed first, and then the Bruce protocol value would be subtracted from that. So in that case, we get a positive mean difference, right? And like I told you guys, whenever you calculate your t-statistics, or if you're looking at mean differences, you're more so concerned with the absolute mean difference, but the sign, again, in these tables is going to indicate which mean was greater. So from there, basically you skip all of this middle stuff, and then we can look at our t-statistic, right? We can see our degrees of freedom is -1 because we only have a single sample. We're just repeating the use of that sample, okay? And then our p-value for our t-test is going to be, again, in this sig column. So again, I'll leave that up to you guys to figure out if that is a significant difference between the means or not. Okay, so as you can see, t-test and SPSS are not super intimidating, okay? As long as you know where to look, you should be fine, right? But we are not done yet. We now have to calculate effect size and sample size, and we're going to do this for data sets 2, 3, and 4. So before we do effect size, we need to have do some calculations. We need to know the mean and standard deviation, right, of our values. And in this case, for effect size, usually the control group standard deviation would go on the bottom. If you don't have a control group, then you would use a pooled standard deviation, which is just taking the standard deviation of all of the values within your data set. Okay, so up here, we're going to do our calculations. So we'll say, we'll just call this x1. So this will be our mean of x1. We'll have a mean of x2. And then because we don't have a control group for this data set number 2, we're just going to put SD pool. right? From this, we should be able to find our effect size. Okay, so these should be pretty easy for you guys to calculate, right? Our average is going to be all of the labels with data label number 1, right, for USA. So that would represent our mean for the US group. Our mean for the Canadian group, right, would be the Canadian people, or if, because we copied and pasted those values, you can just start from data label number 2. Either way works, right? Our standard deviation or pooled standard deviation is going to be all of our data points within our data set. And then our effect size is just going to be the difference of the means divided by the standard deviation. Okay, so in this case, you can either do an absolute value function if you're looking at the absolute value of the difference, right? For me, I just visually say which mean is larger, and I put that one first. Okay, so for order of operations, these need to be in parentheses. So we'll take the larger mean first, minus the smaller mean. That way we end up getting a nice positive number. Okay, whoops, parentheses there. And then we're going to divide by the standard deviation, or the pooled standard deviation, which will be this box, and my Excel is covering that for some reason, so pretty easy to calculate as far as the effect size goes. Okay, so I took a small pause in the video so that I could bring up our effect size slide in the PowerPoint, just so you guys can recall how we actually evaluate effect size. And of course, PowerPoint is being slow now. But if you can see, I know it's a little bit small, but effect size is kind of, at least value-wise, is kind of similar to when we look at correlation coefficients as far as strength goes, right? So pretty much anything between 0.3 and lower indicates that we're going to have a relatively small difference between the means relative to what we're actually measuring. Okay, 0.5 is going to be more of a moderate difference, or anything between 0.4 and 0.67 area, and then anything 0.8 and higher would represent a large difference. Okay, so given that information, right, we can see our effect size that was calculated in data set number 2 comes out to 0.58. So we could round this to 0.6, which would indicate that we have a relatively moderate difference, right? And when we look at the actual difference between the means, 71 to 79, right, VO2 wise, that's a difference of about 2. Okay, so in the grand scheme of things, it's kind of up to the person to decide if that difference is actually large or not, but relative to our example and our calculation of effect size, we're going to say this is a relatively moderate difference. Okay, and PowerPoint is now not working, so I'm sorry. But then we also are going to calculate sample size. Okay, and we're only going to do this for the VO2 max test and the VO2 estimates data sets. Looking for a power of 80%. Okay, so if we look at our sample size calculation or equation, SD, again, standard deviation. If you have a control group, you would put the control group standard deviation. If not, we use a pooled standard deviation, similar to how we used an effect size. Okay. We also need to know the z-score relative to our alpha for the test we're using, and then we need to know the z-score relative to what beta would be. In this case, this is going to represent the z-score that would exist at our power level, pretty much. Okay, so all of this over, and this is going to represent, or delta represents the difference between the means squared. Okay, so delta usually means change or difference. So with that, we're going to use what we've got already. We have the means and we have the effect size, right? So basically all we need in addition, maybe we can calculate the mean difference so that we've got that column locked and loaded. So again, I like to do the absolute difference, that way we have a nice positive value. So I'll do the larger mean minus the smaller mean. Okay. We also need to know z alpha, which for this test we used a 95% level of confidence, which means that our z-score, right, associated with a 95% level of confidence usually is 1.96. Okay. Down here I hinted, right, if you're finding a z-score that gives you a power of 80, right, this is going to be relative, if you recall to the lecture, right, the area to the left of where our alpha is, right? It kind of measures the degree of crossover that we have between our two mean or sample distributions. Okay, so when you look this up in the z-table, you want to look for a probability that's as close to 0.8 as you can get, but that's not going to be less than 0.8. Okay, because remember, power is going to be 1 minus the probability that you would make a type 2 error. So the higher power is, the better, right? But we don't want to underestimate what the z-score would be, because that would mean we're kind of compromising for a lower power, which we don't want to do. Okay, so I'm going to go ahead and open up my z-table. I think I opened up every table except for the z-table. But pretty much we're going to operate on a positive scale just because that's a little bit easier for our calculation, right? But you can see we kind of have this difference up in here, right, between 0.79 and 0.823. Okay, remember we want more power, so we're going to go with a higher number, which in this case would be at this location on the table, so that would give us a z-score of 0.85. Okay, so I'm going to go ahead and minimize that. That would indicate z beta, or the z-score associated with power, is 0.85. Okay, from here we now have everything we need to calculate our sample size, and this is just plug and chug pretty much. So the top of our equation, or numerator, is 2 times the pooled standard deviation. So we're literally just going to do a cell reference to our pooled standard deviation. If you put a little caret and a 2, that is the function for squared. And then we're going to do times, more parentheses. Okay, we have z alpha plus z beta. Remember, both of these should be positive because they're just indicating what the absolute distances, okay, or from their respective means. And we're also going to do a caret with a 2 to square that. Close the parentheses for the numerator, and then we'll divide by the mean difference, which we calculated, also squared, and you press enter. Okay, so this is our sample size, example, right? So I can type those above. Effect size. This one is sample size, so we don't get them confused, right? And basically what this is saying is that in order to attain a power of 80, which is usually acceptable, right, we would have to have 46 people per sample, okay, or 46 people total that we are measuring to get fairly significant results. And you can tell, I think it was indicated in our sheet, right? But we had 25 individuals per sample, and that gave us a relative effect size of 0.5, right? So sample size is generally going to be somewhat related back to effect size, but generally this is just saying like how large does your sample have to be to where you have generally minimized your type 2 error or increased your power to an acceptable amount. And remember, as power increases or as type 2 error increases, we get the opposite effect in our alpha, right? Well, alpha is set in this case, so that's why we manipulate power, or basically manipulating how much type 2 error we would allow, and we can see what our sample size would need to be in order to have decent results, okay? So what I'm going to do is just copy this general setup because we need to do the same thing for data set number 4, okay? So the only thing is that these numbers are not going to be relevant to this data set completely. So for the mean of the Bruce protocol, you can see the area isn't quite right. So we're just going to make a few adjustments here and there. And then standard deviation should include both of these measurements since we're not identifying a control group. Okay. And then effect size, you can see it came out negative, right? And that's because the order in this is that my smaller mean goes first. So basically all we have to do is change the cell references so that the larger mean is listed first in the equation, minus the smaller mean divided by the pooled standard deviation, and we should get a positive effect size value. In this case, we have an effect size of about 0.3, which in itself isn't that large. Okay. Our mean difference, again, I like to switch these so I have a positive value. So I'm going to list my larger mean first, which is indicated by the blue box, minus the smaller mean. And we saw in SPSS this should be 1. Okay. My Z alpha isn't going to change because my confidence level of confidence didn't change, right? Net 1.96 is associated with a confidence interval or a level of confidence of 95%. We're still saying we're shooting for a power of 80%. So Z beta should be the same. Okay. And then all we have to make sure is that our cell references are correct in our sample size equation. So we have 2 times the standard deviation or the pooled standard deviation squared, right? And then we have Z alpha plus Z beta squared divided by the mean difference squared. So this is telling us that we should have a total sample size of 194 people in order to accept our results. So in this case, that would be a limitation of this study if this was a published work, right? Just say that based on the availability of the convenient sample or how many people were able to be collected at a given time, possible limitation could be that there aren't significant results, or there are significant results, or if there are significant results, we have to take them with a grain of salt just because the sample size wasn't large enough to have a big enough power. So there is a chance that a type 2 error could have been made. Basically is how we review that. Okay, so that's our data set number 1 for our calculations. The last thing you're doing is creating a bar graph with error bars for the VO2 max testing, squatting test, and VO2 max estimate. So this would be data sets 2, 3, and 4. Okay. All of you should know how to make bar graphs by now. Okay, error bars I believe we did in the first lab. The one thing I will say to be careful of is that because we had copied, right, Canada's measurements down here, just make sure that when you're pasting your bar graph, you're actually highlighting the correct values that should go into the graph. Same thing with the rowing cycling example. We pasted our cycling people below the rowing people. So again, make sure that your data that goes into the graph represents what was actually measured. Okay. But if you guys need references to how to do error bars, I'm pretty sure it's in activity 1, so you can look back at that video. There are shortcuts in the description section of the video on YouTube, so it should be pretty easy to find in the video. Okay, so for the review, I'm going to kind of just go through the instructions for this part. For the most part, it should seem familiar to last week's stuff. So in the Review 1 worksheet, you're going to run a bivariate regression analysis. Okay. We're using the data gathered from long jumpers to find a regression equation that estimates long jump distance based on max sprint speed. So the way that this is worded should indicate what your independent variable is versus your dependent variable. Okay. You'll make note of the equation that you would use, the correlation coefficient, coefficient of determination, and the p-value for the slope of your regression line. Okay. And then you're going to use the regression equation that you find based on your processes in SPSS. Right. So I've given you some data. Put that into SPSS, run your bivariate regression. You get a regression equation, and then you're going to use that equation to estimate the jump distance for someone with a sprint speed of 10.67 meters per second. Okay. Additionally, you're going to do a second calculation where you use the equation to calculate the sprint speed that is likely needed to jump 800 centimeters. So this one is, or these two questions are basically just looking at how do you manipulate an equation to get the answer that you want. Right? So in the answer sheet, you'll see you're listing the regression equation, correlation of coefficient, right? All of those values that I mentioned you take note of. What the p-value indicates about the relationship between the variables. Okay, remember p-values are assessing null hypotheses. So when you're considering what the null hypothesis is, right, think about what the p-value is for, or what it was calculated for. Okay, and then your predicted values will go in these last two boxes, or last two blanks. Okay, for our review data set number 2, let me pull that up. Okay, you're determining if the distribution of the data is normal. Okay, and you can use calculations via SPSS or Excel. I've taught you guys how to do this both ways. And you can check back to activity 3 if you don't remember. Most of you actually did really good on this question on the exam, so I'm hoping you remember how we assess normality or assess distribution shape. Okay, so you'll run those calculations given this data set, and then you have a small set of questions to answer based on the normality. Okay, so you're going to indicate if we have normally distributed data, how you objectively know. Okay, so use any calculations that you have done as support for your answer. Okay, and then you're going to use the data that's given in that sheet. And we're going to say, I forgot to change the wording on this question, but we're looking for the exact percentile. Okay, so this is just a throwback. Hopefully you guys remember the difference between an exact percentile versus an estimated percentile. Okay, but it would be relevant to a 1RM score or data score of 123% squatted. Okay. The last review set is going to be looking at, pull up my instructions. You can see review number 3 has 2 spreadsheets. So we have data that we're going to use to put into a multiple regression analysis. Okay. I've highlighted that you'll use a backward elimination as well as a hierarchical method. Okay, in the hierarchical method, you're just going to put in all of these in that block 1. Hopefully block 1 means something. But when you put your variables in, obviously you're going to separate your dependent variable from your independent variables. But for the hierarchical method or enter method, you're just going to put all of the independent variables into the regression all at once. Okay. So with the output that you get, you should be able to build some equations and find some R-squared values. And then similar to our previous activity, you're going to find correlations between the actual batting averages and predicted batting averages using the cross-validation set. So this is different sample compared to what is in this data sheet. Okay, and basically you're going to use the equations that you found, right, using backward elimination and hierarchical method, and then apply those equations, right, based on the data that are presented here, and then compare whatever the predicted values that you get from the use of those equations to what the actual averages were for this cross-validation set. Okay, so as far as answers go for that last review set, the format is pretty similar to last week's example, or at least the practice problems. However, last week we didn't have a backward elimination example, so I wanted to insert one in here. And then we have some questions based on how you read and create the model. So looking at the flowchart video from last week might be helpful in figuring out this section if you haven't watched that yet. And then lastly, we're kind of looking at how the cross-validation method is indicating kind of what regression model is the best. Okay. So yeah, that's pretty much it for activity 6. It's not too hard of a week. Again, I think the review is key. When you turn in your submission, just make sure you have 3 components of your submission. So you should have the SPSS output with all of your t-tests in it and regressions. You should have your completed Excel spreadsheet, and you should have a completed answer sheet, which should be this lovely guy here. Okay. If you guys have any questions, please let me know. This is a section where things start to get a little bit more complicated, and if you don't have your information organized, it can be difficult when you're looking at questions. It's very common for people to go blank. So shoot me an email if you have if you get stuck. If you need to see an example run out in real time, I'm always happy to make a short video based off of your question. Obviously, I can't make videos for everybody, but if it's a commonly asked question, I'm definitely happy to make a video or do an extra Zoom chat with you guys. Okay, so good luck, and this will be due next Monday on the 19th by 11:59.